All right, so you should see up on, excuse me, Canvas, got two assignments, so that Connect assignment and the individual assignment. So made this due date pretty quick, so a week from today, because the only things that you'll have need for it, well, sorry, the very last question we'll cover on Monday of next week, but everything else we'll done this week. And I think if you just wait a long time to do this, it's almost like what we did in Excel for the individual assignment. And so I don't want you to wait a long period of time, because then I know that a lot of you are going to go back and have a lot of questions, right? So I want to try to keep that. I know that material is kind of the most relevant, so the most recent. So maybe due date a little bit earlier. That Connect assignment kind of goes into some topics that we'll cover even towards the end of next week. Okay. So I would start working on the individual assignment. You'll look at some things on it, and it says log normal. That's what we're going to be talking about today. But all the normal distribution stuff is everything that we did last class on Wednesday in Excel. Okay. And that'll be kind of using your data set kind of from earlier this semester. I know we haven't kind of used that in a while. Usually we use those a little bit more towards the end of the semester. Okay. Any questions from you before we keep kind of jump into things here today? All right, so we've got a couple distributions we'll talk about today. And the one is kind of related to the normal distribution. We'll talk about that in a second. The other is related to something we already talked about, which is this Poisson distribution. So we kind of think about this as an exponential distribution. It really just looks like a very extremely right skewed distribution, right? We can't see anything below zero. So this is kind of the idea of the Poisson, right? You can't see negative successes, right? But you can see zero. And then you can see a higher number of occurrences of things. So zero kind of moving up. The only difference is, unlike the Poisson, it's now continuous. I can see 1.359. I can see 0.24, right? But it kind of has the same idea that there is going to be some average rate that we typically see. We'll kind of think about that as lambda. Okay. So if I have this average rate lambda, the way I can find the expected value of my exponential variable, right, where I can find the mean, is just simply 1 over that lambda. So that's something I'd have to be given. So we'll look at an example here in a second. I think it'll make a little bit more sense. But generally, just the general form is going to be the mean is 1 over this lambda we get, and the average rate. The probability mass function, right? So unlike we had to do with the normal distribution, right? That was a very complicated function. So someone's already done all the integration for us. Here, if we want this probability mass function, or this cumulative kind of density function we're going to think about, it's giving us the probability of seeing a certain value for x or anything below it. It's simply going to be 1 minus e to whatever that negative, or e to the negative, whatever that lambda is, times the x value you're interested in. So you can kind of think about it here. It's almost like, here's our exponential distribution. Maybe here's the cutoff value for x, and we want the area under the curve. That equation would give us that area under the curve. Okay. So it's a similar procedure of what we're doing, since we don't have to use the table now, we can use an actual function. Okay. So let's look and see how this plays out. So we've got this example where I've got a car battery, and the probability it lasts a certain number of days decreases, right? So kind of think about this as I use the battery more and more, I know that the number of expected days that it's going to last is kind of falling towards zero, right? It can't last forever. And the more I use it, that life expectancy goes down. So let's assume that someone tells us that this average rate is what, 2,000 days, right? So on average, we kind of get that a battery life is 2,000 days. So what we want to do is find the expected value. Okay. So what we're given, let me see if I have it here. There we go. I'm going to skip ahead. I'm going to come back to this, but what we're given is the expected value, right? So we're told this expected value for the number of days this battery lasts, or the expected value of the random variable is another word or another phrase for its mean. This is going to be equal to 2,000. Now the problem is that probability mass function had lambda in it, but we aren't usually given lambda, right? So we are given this average rate, we're given the mean, you think about, we have this data set, like we could have like all these car batteries, and then each one, how long it lasted. We could find the mean of that column of data, but we can't observe lambda. However, we know that if this is the case, right, I could rearrange this a little bit. Right, and lambda would also be 1 over the mean. Okay. Well, now I can plug in that mean I was given of 2,000. So I've got my lambda is going to be 1 over 2,000. So you're usually, in these examples, if you have an exponentially distributed variable, you're told the mean, or you're given mean, or you can calculate the mean from some data. However, the probability density function doesn't need the mean, it needs this lambda rate. Right? In fact, actually, I could actually just change this function a little bit. Well, hold on, I'll hold off on that. So we can calculate from that mean, calculate lambda, then we'll have lambda to be able to plug into this cumulative density function, right? So now I've got 1 over 2,000, and I can plug in, okay, what's the probability the battery lasts more than 6,000 days? Plug X is 6,000, right? What's the probability that it lasts more than 100 days? X would be equal to 100, right? E is just this natural number, and so I can kind of figure out what those probabilities are. Now, what's one way I could manipulate this formula, maybe, so I don't have to do this step? If lambda is 1 over the mean, how could I rewrite this function? Right, I could just plug that value in there, right? 1 over the mean. You know, that's what I'm going to end up doing anyways, right? But it kind of avoids kind of this intermediate step. I don't have it written up there that way because in general, we want to think about trying to figure out what that lambda is first. Just kind of breaking it down to parts makes it a little bit easier. But if you wanted to, you really could do this, right? You're just kind of substituting formulas in there or equations in there. Any questions up to this point? Okay. So we've got this lambda. We could then think about what's the probability that this car battery lasts more than 10 years, right? So I think this one is a little bit harder because I think that the average life was in days, right? But here, if I want to know, does it last more than 10 years, what would my X value be? I'm thinking about days here. How do I turn years into days? Yeah, right. At least I'm kind of being a little bit, I guess, cheating there a little bit. I'd have to figure out like leap years or something like that. But for the sake of this example, we'll kind of use that 365, right? So we now have this X value that we're interested in. What's the probability it lasts more than 10 years? All right, so if we go ahead here. Well, if I ever want the probability of being greater than a certain number, it gets kind of a little bit tricky. I can kind of write this out, right? So this would be the probability that X is less than or equal to that 3,650. So we had what? Negative 1 over 2,000 was our lambda value. We'll then multiply that by the X value we're interested in. But notice, this is what gives us the probability of being angle. There we go. That would give me the probability of being less than 3,650. If I want the probability that lasts more than 10 years or greater than that value, same kind of idea, the area under my curve is always 1, right? So if the area under the curve is 1, I'll just do 1 minus that. But I know that area is this here. Well, 1 minus 1 cancels, and then minus a minus makes that positive, right? So this one is actually a little bit easier to kind of find the probability being greater than a certain value because you actually do have a formula that can give that to you. You don't have to necessarily rely on the complement rule, although the complement rule is what allows you to know that finding the probability being greater than a certain value is this equation. Yeah. No, you sure? All right. Any other questions on that one? So now it's a matter of plugging those values in. All right, so plug all these in. All right, we then could subtract whatever that answer is from 1, or we could just know that ahead of time. 1 minus that is just going to give us that positive e to the negative lambda times x, sorry. Questions on that? That's not too bad. We won't use this a ton kind of moving forward, but I wanted to introduce that we can see these different distributions. If we have a data set and we create one of these bar graphs and we see that it looks like a really, really extreme right skew distribution, that might allow us to think about this as, oh, this is an exponential distribution. Now, one that's really similar to that we're going to focus on a little bit more, and I'll actually show you an example in Excel today for it. Oh, there we go. Is this log normal distribution? This is complicated, right? But I'll try to kind of walk through this in steps. So what we're going to do with a log normal distribution. First of all, can I erase this? Everybody got this right? So we can kind of think about it as though we've got this data, we graph it out, right? We look at the distribution, and it has kind of, for very very high variances, it kind of looks similar to an exponential. But as we kind of see that standard deviation, that variance is a little bit smaller, it just looks like a really right skew distribution, but it at least has kind of this left tail, right? The exponential didn't have a left tail at all. Okay. So if we've got this log normally distributed variable, which kind of looks like this right skew distribution, then we're going to have to do a little bit of work. So I'll talk about these equations in a second. But what we're going to be able to do, so if I had like this data set, right? I could calculate the mean. I can think about this as maybe the mean of my y variable. Right? I could also calculate in Excel that standard deviation of my y variable, or we're using kind of the notation sigma there. Okay. So instead of kind of using this in parentheses, I'll probably write it out kind of like this, just using subscripts. Okay. So if I've got the mean and the standard deviation of this y variable, the problem is this y variable is log normally distributed. So what it means when we say it's log normally distributed, that looks so, actually no, I have this wrong, don't I? What do I want here? I want, oh, I didn't put in the slides. You can see. Okay, so I'll do well, I don't know this. Okay, no, this is right. Actually, I second guess myself from my memory, but I got this. So this is log normally distributed. So the reason why we use that terminology, the reason why I confused myself in my head here. So this x variable is the one that is normally distributed. Okay. Now we can't observe that x variable. We're observing this variable y that's in the data set. However, we know that this hidden variable x is normally distributed. So the reason why we say y is log normally distributed is because I don't know what your most recent math class was, but if I wanted to solve for x here, how would I do that? Does anybody know? No. Yeah, right. So I would take the log, the natural log of both sides, taking the natural log of e. Oops, sorry. Kind of cancels out. Actually, bring this to the forward, and so, or actually, sorry, you bring the exponent in front. Log of e is 1, and so we've got that the log of y would be equal to x. Well, this is great, right? In the sense that we know x is normally distributed. So if we have the log of y, right, we know that new variable that would be normally distributed. So if I had the original variable y in my data set, I could like create another column where I took the log of y. And then if I graphed out the log of y kind of this distribution, it should be normally distributed. But it's only normally distributed after I take the log. So it's log normally distributed. Now that's kind of where that comes from. But all we observe is y in the data. Okay. So what we're then going to do is we need to know, okay, what's the mean? I cannot write these markers today. What's the mean and the variance of my x variable, right? Because if I've got this log normally distributed variable, I can then start to, if I convert it into a normal distribution, right, by taking this natural log, well, now I could start to think about finding the probability of being above or below certain values for this log normally distributed variable. Because if I get to a normal distribution, I can get the mean and I can get the variance, well, I can turn it into a standard normal distribution and use my table. Okay? So that's ultimately where we're going. The problem is I first have to calculate the mean and the variance of this normally distributed variable I can't observe. The equations that we'll use to do that, and that really expected value of x here, I'm going to give it some general terms. This really, I think it will help to think about this is going to be our expected value or our mean of x. Right? So if you don't want to think about this as expected value, this is the equation that gives us this mean of x, right? And then the other equation, I put standard deviation there because ultimately when we start doing z-scores, I'm going to need my standard deviation, right? The only difference there is if I wanted to calculate the variance, I just wouldn't have this square root. Right? So I guess, showing you the standard deviation equation, I'm really showing you the variance equation kind of as well, right? You could just think about you wouldn't have the square root there. So these are the two equations that we're going to use once we have the mean of x and the mean of x and the standard deviation or the variance of x. We can then turn different values for x into a z-score, look it up in the table, and find the probability that we're below a certain value. Now, the only problem is we only observe the values of that y variable, right? So when we think about plugging in values for x here, I'll use the example of income. Let's say income is log normally distributed, okay? I can't simply plug $100,000 into this because this is the mean and the standard deviation of this x variable, right? So in order for me to have an x value, when my original variable was income, my original y variable was income, I have to take the natural log. So if it helps, you're actually going to be thinking about different cutoff values for y, maybe $100,000 of income, but to convert that cutoff value to this log normally distributed variable, we'll have to take the natural log. And I'll show you what that looks like in Excel here in just a second. And then we subtract the mean of x, the standard deviation of x, because we know it's a normally distributed variable. This can turn it into a z-score. You can then look that up in the table. So another, actually I'll come back to this, but here I'll put some values to it and we'll just kind of talk through. So let's say I've got this log normally distributed variable, which is the expected duration of your phone, right? How long your battery lasts before you can recharge it. Right? So, someone tells us, or we observe the data that's log normally distributed, and we can, in the data, right? Like I have this data set, maybe of 100 different phones, and I kind of allow people to use them and see how long did it last, right? Like how many minutes or how many hours, however the measure is. All right, so I'm guessing it's minutes. So 500, right, was the mean I could calculate from this data set. And the variance I calculated was 5. So that was the original variable y I can observe. Right? The problem is I know y is log normally distributed. So I want to be able to use that normal distribution. I don't have a log normal distribution table I can use. So what can I do? Well, I can convert that mean and variance I can observe, right, into the mean and the variance of x. Okay? So notice here, this is just the mean that I observed, and here's the variance that I observed. Once I plug those in, right, I'll have my values for the mean of x and the variance of x. So I'll have these two values. Right? I could then think about, well, what's the probability that I see this battery lasts above or below a certain number of days? So I don't think I have it on here. So I'm going to do this work for you on the board. So this is just really plugging and chugging. Right? You've got these equations in front of you. Once you calculate the mean and the variance from the data set, plug them into these formulas, you'll get your mean and your variance of this unobserved normally distributed variable x. From there, what are we going to do? So now, kind of go along with this example, we've got what? X is normally distributed 6.21. 0.00002. Okay. What is this going to be? I think so this is my variance. This is you think about as nope, sorry. Here, my mean and my variance is x, right? So if I want the standard deviation, be what? The square root of 0.00002, which is, so if I squared something, so say, anybody want to help me out with this? Nobody? All right, well, this one.
Yeah, 0.0044. 45 actually.
So we've now got our standard deviation, because once we get to that z-score equation, we know that we're going to need that, right? So I just kind of turning that variance into my standard deviation. So maybe the question becomes, what's the probability that I see this phone battery or my phone duration be more than, sorry, let's do less than 200, just to kind of keep this nice and easy. Well, I know that if I want to use that normal distribution, I can't use the value 200, right? Because we go back to what I had before. I know that my different x values are actually the natural log of whatever these y variables I'm interested in. And I'm writing log here. I should really be, we're not using the base 10, which is when you write log. I should be using ln here, but for the sake of this class, we can use those interchangeably. We're not going to do anything with the 10 base log. So I take that natural log, right, of y to get these different values. So if I'm interested in the probability of seeing something below 200, the actual value I need to use for this x variable would be the natural log of 200, right? Well, now once I have that, I can convert this into a standard normal distribution, turn that natural log of 200 into a z-score. How could I do that? I take that x value, right, the natural log of 200. I'd subtract, where is it? The mean of x, which was 6.21, divide by, where is it at? Standard deviation, 0.0045. Now, this one, I think the numbers I chose, this is going to be a really ridiculous one if I had to guess. I'll use my calculator in front of me here just for a second. So, all right, 5.29. I'm looking at that, right? It's going to be a lot of standard deviations away, right? If I did kind of look at that, because what this gap in between is about 1. Well, if my standard deviation is 0.0045, I mean, I've got what, 100? So yeah, I've got over 100 standard deviations away. This is basically going to be like this area to the left. If I'm like 100 standard deviations to the left, like negative 100 z-score, the area to the left would be about 0. Right? Our table only went out to -4. So if I had a negative 100 z-score, man, that probably is going to be really close to 0. Okay. Seeing some confused looks. Any questions? What was, or are you not sure what's confusing, or we have any questions here?
I think it's all the different equations.
Yeah, so let me try to kind of show this to you in Excel with some actual data. Maybe it'll help a little bit. Okay. So we're working with this data last class, and I can come back and we can work through another example as well. And I think we did temperature. So I'm just going to use the rain data, and I don't really need any of this for right now. Oops. I want to make a different point. Okay. There we go. Keep my control. I'm just going to delete all this. Okay. So let's think about what we have over here. We've got all these different months and the rainfall. We also have annual rainfall. I'm just going to use annual rainfall, to be completely honest, because it's the one that's on the far left. And so we can kind of see what we're working with here. Okay. So I don't believe, if I graph this out, I think annual rainfall is very close to normal distribution. I didn't go through, but it's very close to normal. We're going to treat it like it's a log normal distribution just for the sake of this example. Okay. So let's assume that this variable that we have, annual rainfall, and we can kind of ignore this column if you really wanted to. Control Shift, hit the down arrow, delete, then go back up to the top. All right, we can kind of delete all that data. We don't need to use that. Okay. So I've got this annual rainfall and this log normally distributed. Well, I can find the mean. And here, I'm going to think about this as the variable I'm observing, if I can type, is y, right? I've got some underlying normally distributed variable x, but y, this variable I'm looking at, is log normally distributed. So I can find the mean and the standard deviation pretty easily in Excel, right? Use that average function, go over, Control Shift, hit the down arrow, then hit. I don't know if I should or if I mentioned this, but when you use that Control Shift, if you don't want to scroll up, if I just hit Enter, it'll close that parenthesis and send me back up to the top. I think I've mentioned that, but just to reiterate it, I'll treat this like population data since I have every single kind of year. Well, got to 2019. I guess I should add in the next last few years. So I'll select that entire column. I now have this mean and standard deviation of this variable I can observe. Okay. Everybody with me up to this point? Okay. So the issue is maybe I want to know, okay, what's the probability if I'm looking at these values? Like on average, I see what, 3.4 inches of rainfall. So maybe I'm really interested, I don't know, I'm in the agricultural sector and, I really need a boom year, right? So I'm like, I need a lot of rain. So I want to make sure that I have a lot of rainfall, but I don't want too much, right? So I might be concerned with what's the probability that I see rainfall be greater than, let's just do 4 inches. So what's the probability I see rainfall be greater than 4 inches? Actually, let's choose it. I think that's going to give us a wild z-score. So I'm going to choose a different value. Let's do 3.5 inches. Still greater than the mean. So we're thinking like, what's the probability I see a lot of rainfall? So we'll start out kind of thinking about, well, and actually I'm sorry. This should have been a y, right? We're thinking about this variable that we're looking at, rainfall. So ultimately what we want is to be able to convert this log normally distributed variable log normally distributed variable y into x, right? So how can we do that? And then we want to know, okay, what's the probability? Not that it's less than 3.5, but that it's greater than 3.5. And if we're looking at this new variable x, I can't use the value of 3.5. What did I say I need to do? Remember, I had to take the natural log of these different values I was interested in for my original variable. I was interested in the probability I had more than 3.5 inches of rainfall, but that's not the cutoff value I need to use. The cutoff value is actually the natural log of whatever that value is. But the way in which we'll talk about it, we'll think about, I'm trying to find the probability of having more than 3.5 inches of rainfall. It's just that in order to be able to use that normal distribution, I have to convert that using this log or this natural log. So the next step is going to be, well, I also, even after I convert it, I need to know the mean and the standard deviation of this variable I can't observe, x, that I know is normally distributed. So actually, let me move this down just so we have some separation here. So these are the next things that I want to calculate. And this is where I'm going to have to kind of remind myself of these formulas. I do not have them memorized. Right? So I'm going to go back to my equations, right? And kind of, I think here, where I use the subscripts on this slide, probably a little bit more useful than these equations here. So I'm thinking about why is this variable I can observe? So I want to take the natural log of the mean that I can observe squared divided by the square root of the mean I can observe squared plus the variance. Okay. So I'm going to go back here. I'm going to try to burn this one into my memory. So the first thing I needed, actually, can I minimize this so that we can see everything at once? That might be helpful. There, I think we can make it work. We don't really need to see the data anymore. So I'm going to use the natural log, which is simply ln, right? So that's the built-in formula in Excel. It'll take the natural log for it. I think if you've got a calculator in front of you, you should be able to find a natural log button on there as well, right? But here we can kind of see what it looks like in Excel. I'm then going to take my mean and square it. I'm then going to divide that by the square root. Well, we've used that function before. That's just SQRT. And then once again, of the mean squared. All right, that kind of carried, that's the raising it to the power of whatever we want here. We just want to the second power. And then adding in my variance. Now, I think I have the standard deviation here. If maybe I could have made this a little bit easier, I could have calculated the variance originally. But if I have the standard deviation, I could just, square that as well, right? So it doesn't really matter however I want to do it there. If I calculate the variance and I just have to select on the cell, if I calculate the standard deviation of my original variable that I could observe, I'm going to have to square it to get that variance. Okay. And I cut this off a little bit. Let me see. Can I make this a little wider so we can see? There we go. Okay. Any questions? Is this starting to make a little more sense how I'm going to kind of proceed through this? So I got the original data. I can calculate that mean and that standard deviation of that variance. But I need to convert that into a normal distribution, and that variable I observed is log normally distributed. So I can calculate the mean and the variance of my normal distribution using those formulas. Here we've got the first one. Oh, what did I do wrong? Oh, I forgot to close my parenthesis. Huh?
You need a parenthesis.
And now I deleted everything right now.
Before the square root, like.
No, right. So if we go back to work, I don't know why. So this is not a pick on you guys because you guys are actually pretty good about it. My other, like my non-honor sections are paired. Like, I don't know if they don't teach order of operations anymore, right? When you raise something to a power, right, it does this math first, right? So you don't need to put parentheses around it.
I wasn't sure if it was gonna take it as, like, if you're raising it to 2.
Plus this.
Yeah.
So, no, if I ever wanted to do that, I would also need to use, like, let's say I wanted to raise it to the 2 plus 3 power. If I raise it, whatever I want to raise it to has to be in parentheses as well. Yep.
I wasn't sure because you can't actually make it like up there.
Yeah. Yep. Yeah, if I wanted to be a little overkill, just to like make sure we're doing, like I could have put parentheses around everything, but it's ultimately we only had one value that we're raising it to, so we didn't have to worry about that. Now, if I was doing something like my exponential, well, then I would need to make sure I had lambda times x in parentheses. Yeah, yep. Yeah.
I don't know what I'm going to use this compared to some other stuff too last week.
Yeah. So for the most part, right, I'll be giving you, you'll be told if the variable you're looking at is normally distributed. If you're told the variable you're looking at is log normally distributed, which is that individual assignment, basically what I have you do is I say, choose one of your variables, assume it's normally distributed. Then we proceed like we did last class and last week. If I tell you assume it's log normally distributed, well, now I have to approach it this way, right? Because I know the variable itself isn't normally distributed. I need to convert it into that normal distribution.
And then once we have normal distributed, we have to convert it to
Standard. And really that's what we're doing here too, right? We're first converting it into a normal distribution, right? That's what we'll eventually get the variance here, but we've got the mean right now. Once I now know the mean, so this was what? 1.21. Well, I need to calculate the standard deviation, but once I have that, now I turn this value I was interested in into a z-score. So the log normal distribution is more complicated. It's an entire added step, right? But once I complete that first step, now it's back to kind of what we did before, right? Now I've got a normal distribution. I can then turn it into a standard normal distribution and then use that table. Is that, I know like if you're thinking about in the homework or things like that, you'll be told what the variable is distributed as, if it's normal or if it's log normally distributed. Does that help a little bit? Okay. Questions on this for you? Yeah.
So then if the mean is 1.21, why are we looking at, why is 3.5 below it on the graph?
So I didn't use 3.5. What did I use?
So
I actually used that natural log, right? I didn't write that number out yet, so if it helps, no, that's a good question, right? In fact, I might have graphed it in the wrong spot. In fact, I did because, sorry, I was just kind of building here.
You're good.
If I'm looking at what was the natural log of 3.5, it's actually going to be. It's a good question. Sorry. Yeah, I just put it up there so we could think about the areas. I wasn't thinking about relative to the mean. So you're right. I really shouldn't have been graphing that until I had the mean, right? And then I knew where it would fall in relation to that. Correct. Any questions on that? Kind of reusing a graph there. So yeah, if it makes a little bit more sense. We want to find the probability of being greater than 3.5. So I had erased this area. I know it's still a little bit. So actually what I want to find, I'll try to get rid of the blue to make it obvious here. I want to find that area. Okay. Just trying to recycle graphs. I should have erased that. Okay. All right. So I need one more thing, which is the standard deviation. So I go down here. Now I've got the variance equation here. So what's the one more additional thing I need to throw into that equation? Yep. So I'll just start out with my square root. I then will take the natural log of what? 1 plus, and this is where I do need to be careful a little bit with my parentheses potentially. I could probably do it overkill, but actually no, here I think should actually be fine, right? I could select the standard deviation squared to get my variance, or probably would have made more sense to calculate my variance instead ahead of time, and then divide by that mean squared. All right, so I'm just getting that equation entered in. So I square these and divide and add 1, take the natural log, take the square root. So all I'm using Excel to be is my calculator here, right? I could do this by hand. I could enter these values in my calculator. You kind of see we get some, it's going to go out to several decimals, so I'd have to start rounding, and it might really kind of screw my probabilities up a little bit. Whereas if I can do this in Excel and just kind of use my cell references, it keeps it out to hundreds of decimals there, and I can get a really precise answer. Any other questions on this? Before we keep moving here. So all I did was enter that equation. Are we having an okay time mimicking that? Yeah. So 0.13-ish, right? Well, now I have everything I need. And I should have known this ahead of time. So I look at this. I was looking at something that was above that mean. So my z-score should be positive, right? I'm going to try to turn this into the number of standard deviations above the mean that natural log of 3.5 is. Okay. How can I do that? Well, our general form of our z-score equation looks like this. Well, I've already found that x value, right? I converted that y value of 3.5, my original rainfall variable. I turned it into this log norm, or I took the natural log to make sure that it was now not log normal, but normally distributed. So I can use that natural log of 3.5 or 1.25, since we kind of already had that calculated. I'll subtract the mean, divide by that standard deviation. All right. Now, once I have that, so let's do that now. So we'll go, z value would be, where is this at? This was where we took the natural log of y, right? Subtract the mean. Now here's where if I divide by the standard deviation, this is going to be screwed up, right? When I'm calculating the z-score, order of operations, I would actually need to make sure I do use parentheses there. Okay. Was that? So the whole reason we were calculating the mean and the variance or the standard deviation of this normally distributed variable x is so we could calculate this z-score, right? We needed to have a normally distributed variable, which we knew x was. So because we can only observe y, we'll use that observation about the log normal distribution of log normally distributed variable y to calculate that mean and the variance of that variable. We can observe x, turn our cutoff value for y, 3.5, into an x value. So just taking the natural log. Now we've got everything that we need. I guess if I wanted to be a little more precise here, sorry. Right? Now I plug everything in and I can get my Z value. Now, once I have that Z value, if I was doing this by hand, I'd go to my table and look up what? 0.29. And then that would tell me the area to these other colors. That would tell me the area to the left of it. I wanted the area to the right, so I would have to still do 1 minus. Now, how can I find the area to the left in Excel? So we did this last class. So here, if I want the probability that Z is greater than this value that I found. So for the context of this example, we can kind of think about this as what's the probability Z is greater than 0.289. All right. Well, I have an equation that'll give me the probability of being less than a certain value or a certain Z value, which was norm dot S dot dist, right? I'm dealing with that standard normal distribution now because I've calculated a Z value. If I tell it that value of 2.89, comma 1, that'll give me the area to the left. But I said I didn't want the area to the left. I wanted the probability of seeing something greater than that, or the area to the right. So I would still need to do what? And I can do that all in one cell. I think last class I broke it down in different cells here. I can actually put this all in one cell, right? So hit enter here. And the probability that I see more than 3.5 inches of rainfall this following year is about 38%. Okay. Do you want to see any of those cells again, or any questions on this? Now, this might take a little bit of memory what I did last class, but let's say I want to find that same thing. Let's say I want to know what's the probability that X is greater than that natural log of 3.5. So let's say I don't want to calculate the Z-score in Excel. It's going to be hard to maybe envision this and kind of combining things we talked about last class with today. What's another equation I could use to do that?
Is it the other one we used?
Yep.
It's norm dot something.
Yeah, so we just used norm.s. Whoops, I forgot my. Come on, get out of here. So I just used the norm.s.dist here because I had a Z value, and I know these Z values are standard normally distributed, norm.s, right? But I had a variable X that was just normally distributed. So if I use the norm.dist and I say, okay, what's that X value I'm interested in? Well, that was the natural log of 3.5. Okay. And then, comma, what's the mean of this variable X? Well, I actually had that right here. Comma, what's the standard deviation of X? I've got that right there. I'll make it cumulative. It'll give me the area to the left. We said we wanted the area to the right. So I would still need to do 1 minus, and you can't see everything here. So let me. Oh, there we go. So this, we'll use those 3 things that we found before. The natural log of 3.5, the expected value of X, or the mean of X, the standard deviation of X. Calculate your Z-score. Those are the 3 things that we need to calculate the Z-score. So it's doing that behind the scenes. Then it looks it up in the table, finds the area to the left, and spits that back out at you. Now we want the area to the right, which is why we then did that 1 minus. Okay. So the norm.dist just kind of skips this intermediate step of calculating the Z-score. Okay.
When would you ever use norm dot dist? When would you ever prefer to use norm dot S dot dist?
Hold that thought 1 second. I want to finish this and then I'll come back to it because it's a good question. Okay. So the only other thing I wanted to point out here is in practice, I shouldn't have been using the natural log of 3.5. I probably should have been using some type of cell reference so that if I wanted to go back in and change it, it automatically updates everything. But that's really a little bit of, I guess, being picky there. I'm just, for your homework assignment, you're going to have 1 value. So if you want to use the value, it's fine. Because it was nice and easy, 3.5, if you wanted to play around with some different cutoff values, using that cell reference would be helpful. Because now let's say I want to find the probability that it's greater than, I don't know, 2 inches of rainfall. Well, that's almost a guarantee, right? I said I could play around with those different values here. I'll keep it at 3.5. So when I post this completed version, we'll kind of have exactly that number that we were using. So before I get to that question, any other questions related to kind of this stuff up here? Well, I know this is hard. So this is not lost on me. I would highly recommend starting that assignment early, maybe taking a look at it. I don't know, even today or over the weekend. Come to me with questions early next week. Office hours have been a little bit buried recently, so I wouldn't mind some company. But start working on that early. This will be a really good template for the log normal distribution approach. So your question, why the hell would I want to go and do more work? The reason why is because once we get to things like confidence intervals, we're going to want to determine the number of standard deviations away that we need to go to get a certain percent. So let's say it's kind of like, we haven't really done this yet, so a little bit of foreshadowing here, but let's say I want to know how many standard deviations away do I need to go to get there to be 0.1, right? In that upper right tail. Well, then I'm dealing with a standard normal distribution. To find that number of standard deviations, I have to use norm.s.dist. So I'm showing it to you here. You wouldn't really have to use norm.s.dist in this context, right? You could skip the intermediate steps, but I want to introduce you to the formula because we're going to be using it later on when it comes to confidence interval hypothesis.
Okay.
But you're thinking about it correct. In this context, why make extra work for myself, right? Questions on this 14? Okay. I'm not going to try to confuse you anymore. But you can do this just to mention it. If we had time, I was going to dive into this, but I'm glad we spent a lot of time on the log normal. You can do it with things that are like, maybe you've got a variable you observe and it follows the distribution, which is the square root of a normally distributed variable. Well, then I could square both sides, use y squared values. I'd have to convert my mean and my standard deviation. So I can do different things, even if it's not log normally distributed. But I could do like if it was square distributed, which isn't like a real thing, but it could be a possible thing that we could say. I shouldn't say it's not a real thing. It's not a common thing to observe, but it could be something that we could do. So I tried to write out the steps here just to be, what you would do when using this log normally distributed variable. So we kind of have everything summarized on this slide. So if you're going back and working on this, this might be kind of a good reference of the steps to kind of follow. Right, first find the mean and the variance of the variable that you can observe that you know is log normally distributed. Using those two equations, convert that mean and the variance to find the mean and the variance of this x variable you can't observe. Think about different cutoffs. Well, you can't use x, you'll have to use the natural log. Sorry, you can't just use y, you need to convert that to x. So you have to use the natural log of that variable y. And then in Excel, we can use that norm.dist function, plugging in those three values to kind of find the area to the left. Okay. All right, so just some interesting stat stuff to end here for today. So just to kind of show you what you can do with some of this stuff. So this goes back to what we were doing last week, which is the normal distribution. So I got really interested, I don't remember what year it was now. It's like years, but it was like what, 4 or 5 years ago. The Cubs got second place in their division, and I think they had won, I forget, ridiculous 97 games, which if you're not a baseball fan, that's fine, but that's a lot, right? That usually wins your division. I was like, how unlikely was this, right? So I went and pulled a bunch of historical data to kind of figure this out. I pulled out what the number of wins for every division winner was from like now to the beginning of time in MLB. Well, back to when at least 162 game seasons. I could find the mean. Once I had that, I could find the variance. I'm interested in this cutoff value of 97. Pretty easy to use Excel to figure out what that probability is. Right? I think here, what was it? The probability that you wouldn't get for, right, if you had 97 or fewer wins, that it would get first place, about 66% chance. So there should have been a 66% chance that they won the division, right? But they actually lost it. Right? So it kind of goes against that logic. And then what's the probability that if you won 97 games or more, that you actually end up in third place, which is what occurred in that year? It's 0.003% chance, right? So you can do this whatever you're interested in. You can go out and grab data, calculate the mean, calculate the variance, and it only works if you have a normally distributed variable, but the number of wins for the division pretty close to normal. Might be a little bit of a right skew there, but it's pretty close to normal. So we can probably get a pretty good approximation of that probability, just treating it like a normal distribution.
This is about.
Yeah.
I haven't looked at any of these out yet, but are we still using the same data we used for?
Yep. Yeah. So you can go back and use the data set. If you don't know where it's at in your computer, let me know. I've got them all in a folder on my desktop.
Should we just make a new sheet with that? Like, just
Yep.
with the graph?
Yeah, you can just make a new sheet, like, sometimes what people do will be helpful is like new sheets, you just call like individual IA1, IA2, right? So you're doing all your work, just copy and paste the data onto a different sheet and then kind of do your work for that second assignment on the sheet. Or you just start with the original data and save it as a whole new file if you don't want to put multiple sheets and kind of build on it throughout the semester. Any other questions for the audience? All right. I think I alluded to something about sports, but maybe I'll save that for next week. So you guys have a fun, safe weekend. Start working on that homework as soon as possible. And I will see you guys on Monday.